Hi, my name is Gary Millett, and this is our last topic, topic number 5 in our short course about sensors. We'll call this sensor network technology. This will wrap up the topic, and let's get going. Now, the genesis of sensor networks comes from several areas. So for many years, Moore's law has predicted correctly the number of transistors that can effectively coexist on a semiconductor chip. It's been going on for 5 decades now. What is not so obvious is that the IC chip's functionality increases exponentially along the same trajectory as the number of transistors, and the cost goes down in a similar fashion, or inversely, of course. So this has brought us to a time when the reduced cost of both computing and communicating electronically opens doors to technological innovations that were not possible several short decades ago. With the advent of powerful but inexpensive microcontrollers, economical and miniature wireless systems/technologies that can transfer large amounts of data quickly, and low-cost sensors that have been micro-miniaturized, we can now instrument the world and do it with increasing fidelity and fineness of detail. In other words, the granularity of our detail gets finer and finer. Now, this is the dream of the scientist and the engineer. To be able to provide dense sensing close to the physical or biological phenomena that needs to be observed and possibly reacted to in real time. Now, the application space for sensor networks, or SNs as we call them, is limitless. And if we are to categorize the application space in a general way, it might go something like this. First, the monitoring of places or areas. Next, the monitoring of things. And lastly, the monitoring of the interactions of things with each other and their surroundings/environment. And this quickly leads us to the concept of cyber physical systems, or CPSs. Before considering CPSs, let's consider the 3 broad categories of applications. First, monitoring places or space. We've been doing this for some time now on a mesoscale, which means globally, through the use of satellites for weather forecasting. With the deployment of sensor networks, we have an opportunity to increase the data granularity or detail. Weather events like tornadoes, hurricanes, and severe storms are still very difficult to predict since they can be very localized. However, the availability of more data points will allow us to build better models and hopefully better weather forecasts. Another area of application in this space is the environment. A lack of clean water is becoming a global concern, as is the growing pollution of our sources of water. Our forests and farming lands are subject to the whims of nature in terms of wildfires and droughts. As I'm speaking to you, there's a wildfire which I believe has been going on in California for over a month. Sensor networks could provide better monitoring of these natural resources and allow for precision agriculture also. On a smaller scale, but with a large energy usage, are our cities and towns. Energy management for these entities is another sensor network application area that will pay dividends in the long run if we can somehow manage our use of energy more efficiently. Our large city buildings and homes are prime targets for more efficient energy usage made possible by sensor networks. Transportation also falls into this category. Also included in this category would be homeland security. Sensor networks can monitor our drinking water, electrical power systems, and the air that we breathe for terrorist threats. Intelligent alarms can warn of impending threats of pollution, power failures, weather disasters, and so on. Sensor networks are the key to maintaining and improving the quality of our surrounding environment. Monitoring of things, well, this broad category includes ourselves as things to be monitored. Certainly, the monitoring of structures will, or at least should, provide us with useful data about the health of a structure and its maintenance needs. Our roads, highways, bridges, dams, buildings, power systems, water supplies, sewers, other utilities, etc., are all candidates for monitoring. Sewers, you might recall, people have been checking sewage for COVID-19. Any infrastructure that exists would benefit by structural monitoring, hopefully to discover small problems before they grow. And as we all know, small problems become large ones. As a society, as we age, healthcare costs and availability become a larger concern. Medical monitoring has become more practical and possible due to the ubiquitous nature of the internet, newer, less invasive medical sensors, and wireless technology. The ability to stay in one's home as long as possible is a desire of the elderly. If you have any parents and you ask them, that's what they'd like to do. Through the use of wired and wireless sensor networks, this goal will become more possible, up to a certain point. Monitoring of the interaction of things. This last category of sensor networks is possibly the most interesting and where a lot of research is focused and the greatest development is happening. Applications like the smart grid and intelligent transportation systems get a lot of the popular press. These are the big or grand scale cyber physical systems that will impact society the most and the greatest number of people as we go forward. They will save energy and lives as they are implemented. Certainly, as the population of the world increases, the demand for resources grows. If the resources are finite, there will be conflicts over energy, water, land, food, and so forth. Additionally, there will always be natural disasters that affect the world's population. Sensor networks cannot solve the world's problems, but they can improve the efficiency with which these resources are managed and distributed and help to mitigate the effects of natural disasters. How about the deployment of sensor networks? Well, since retrofitting is very costly, most believe that sensor networks will be implemented using wireless technology. These wireless sensor networks, we call them WSNs, have certain technology constraints. The sensor must be very low power devices, since either battery power or environmental energy harvesting will be needed to supply their power. They will not be able to run continuously, but like a cell phone, will have periods of time when they are sleeping to save battery power. Most wireless sensor networks will have operating systems and application software specifically designed to conserve power. Not all the nodes operate simultaneously, and whenever possible, wireless sensor networks process data within the network before sending it onward. That would be miscomputing. An example of this type of operation would be the calculation of an average temperature. One might say, what is the need for a sensor network if the data from all the nodes is not being used? So the answer to that question is data from all the nodes is being used to perform calculations within the wireless sensor network. Another example of this type of operation would be to send only the highest or lowest temperature, or an alarm if the temperature dropped below a certain level or went above a certain level for any set number of nodes. Also, during operation, the sensor network must relay information from node to node in the most energy efficient manner. Switching gears a little bit, for intelligent transportation applications, vehicles will talk to one another wirelessly by setting up ad hoc networks as needed, and those will be based on proximity. Vehicles will also share or get information about road conditions from roadside transceivers or roadside infrastructure like traffic signals. We don't see it too much around where I live here in Massachusetts, but during the winter you're bound to see news reports of massive pileups of cars, either caused by fog or a sudden snow squall. That's the type of information we'd like to transmit to cars to prevent those types of events from happening. Medical applications will also rely on ad hoc wireless networks within the home or apartment to connect to a gateway router for the collection of vital signs and more. Smart grid applications will rely on the energy-consuming appliances in one's home or apartment, and also the electrical vehicle in the garage, to set up ad hoc wireless networks with a management system and the electric meter. The electric meter will communicate wirelessly on a need-to basis with a pole-mounted access point, which will wirelessly backhaul aggregated data to the electric distribution system or the meter will establish a cellular connection and use it as needed. All done automatically. The architecture of various typical wireless sensor networks will be covered later in this course. The reader might recall that the IEEE 802.15.4 standard, which we call Zigbee, was designed to support many of these types of operation that have been described here, and IEEE 802.15.6 has been designed for medical or healthcare applications. So this ends our coverage of sensor network technology. The reader may find many video clips related to sensor networks and wireless sensor networks on YouTube. Here's a link for an example.